Welcome, folks. We are going to talk about building and deploying APIs with serverless CI/CD. I am Atul Bargaze. I am Principal IoT Architect. Rahul?
Hi guys, my name is Rahul Sareen. I'm a senior IoT architect with AWS Professional Services. Atul and I, we both work in the same team, helping customers out building IoT solutions at scale. So Atul, what do you think people listening to this talk will take out, maybe one point that people will take out of this talk?
Just 1 point. You want just 1 point, huh? So if they were to take just 1 point out of this talk, I would say to make a note of how easy serverless makes to build and deploy your applications, allowing you to focus more on your applications and leaving all the undifferentiated heavy lifting, if you will, to AWS. And that gives you more time to work on the next big idea that you are working on right now. So here's the agenda we are going to talk about today. We will start with a API, application programming interface, or a contract that we will be explaining to you the application about. It's a Swagger spec that we'll be starting with, which represents a contract in a RESTful world. Then we'll talk about traditional application to level set the baseline for our serverless application. We will show you what it takes to transition from a traditional application to a serverless application. We'll talk about developing, debugging, and deploying a serverless application in a new way called SAM way, or serverless application model to be precise. We will then talk a little bit about debugging and local development of this application. Then Rahul will give you some introduction into serverless CI/CD pipeline. And towards the end, we'll leave some time for lessons learned and best practices we have come across over a course of time building lots of serverless application. So here's our contract, or the Swagger spec that we are going to demo the application with. And the contract is for a note-taking application. It's a straightforward application involving management of notes. And with this notes-taking application, we are going to demo the concept of a typical application and how we can transition it to serverless application. This API demonstrates creating nodes, listing existing nodes, updating a node, and deleting a node that exists. So pretty standard CRUD type of application, create, read, update, delete, that you would come across extensively in your API development process. So let's start with a standard application that you would be writing today without serverless concepts in it. And we are going to look at a Node.js, Express.js application. But nothing in this session should confine to Node.js or Express.js framework. The concept should be applicable to any language of your choice, whether it is Java, Python, or Ruby, whatever it might be your favorite programming language. So a typical Node.js, Express.js application, user makes a request into an Express.js application, which acts as a router to your HTTP request, and the requests, they get routed to various endpoints that we are seeing over here. And these endpoints are for nodes creation. There is a post verb which creates a new node in the system. Then there is an endpoint for getting existing nodes or listing those nodes. There is an endpoint for getting specific node by its title, and updating a node, deleting a node. So all the scenarios for most common APIs are covered here in a note-taking application. And then the application writes the actual objects to some sort of a persistent store behind the scene. So that's your typical application. Now, this application is all good, But then you have to do this for a server-based application. You have to make sure your application is horizontally scalable. You have to make sure that your application is load balanced. The database that is holding all your domain object is highly available. It is redundant. And
Yeah, you wouldn't want to do that.
yeah, exactly. So we thought you would be happy spending more time developing your APIs than making sure all these things are taken care of. And that's where serverless comes into picture. It is almost like a magic bullet. So with serverless, as the name suggests, there are no servers to manage, even though behind the scene there are a lot of servers, as you would expect. Flexible scaling is built into it. You don't have to worry about it. You don't have to implement anything. High availability is also not your headache. It's up to AWS to make sure your application is highly available. And this is a big one. The pay as you go is most important business criteria for a lot of people choosing serverless framework. And the reason for that is most conventional data centers, 30% utilization is considered a decent utilization. If you're writing an application, you'd be spending tons of money to make sure that application is highly available, is able to handle the fluctuating scale of requests that is coming in. With serverless, you don't have to worry about pre-allocating those servers, and you pay only as your application needs demand.
So Atul, are there any AWS services or what AWS services basically fall under the serverless spectrum?
So the AWS services that fall under serverless category there are quite a few of them, but the most important are API Gateway, Lambda, DynamoDB, AWS IoT. There are others also, but these form the crux of most serverless service portfolio.
Nice.
So let's transition to serverless application now. In serverless application, like any application, user makes a request, but as you would notice, the request now goes to API Gateway, and API Gateway then forwards this request to a serverless construct, AWS Lambda. Now, AWS Lambda is the compute engine for the serverless stack, and this compute engine can look very similar to your typical application that you are writing today, if it is well architected. And we'll talk about that a little bit later in our presentation. Then this Lambda routes the request to different endpoints. Again, similar to your traditional application, it routes to endpoints for creating nodes, getting the specific node, listing node. It looks pretty similar to your existing application. And then the application would store the state in some sort of backing data store.
So Atul, this is really cool, but what's the advantage of using API Gateway if Lambda is handling all the logic?
That's an interesting question. So the reason we need API Gateway behind our compute engine, or behind actually the thing that processes our request, is for a couple of reasons. First, it gives you a nice separation from your backend infrastructure to the external world. So that can act as your gatekeeper. Then you can meter your applications. You can even set throttling limits on how many APIs can be called by a particular application. You can vend out API keys to different types of application. So that gives you a visibility into the requests that are coming in through the external sources.
That's cool.
So with serverless, you have to do a lot of infrastructure creation and updation. And that's where a construct called serverless application model comes into play. With serverless application, you are able to simplify creating and updating serverless resources quite significantly. So it simplifies the cloud formation or the infrastructure creating templates that you were writing before significantly, and allows you to focus on your serverless applications, serverless APIs. And it supports configuring of Lambda, API gateway, DynamoDB, event sources. You could do these things with CloudFormation, but it used to be pretty involved and you would end up spending a lot of time doing that. Serverless application model simplifies those things significantly, and you are able to quickly get done with your resource creation needs and start focusing on your APIs. And another neat thing serverless application model, or SAM as it is called pretty extensively these days, is you are able to test your applications locally with a module called SAM local. So you can develop your application, test them locally, and then when you're sure your application is behaving to your specification, you can deploy these applications behind the scene to the cloud. So with that, let's jump to a demo and let's see everything in action. You have seen a lot of things, you heard a lot of promises. Let's see how it looks like actually in the code. So we will walk through the code, we will show you the application, and we will show you how the application looks like in a serverless world. Here's the structure of a serverless application. And a typical serverless application, you would have infrastructure related things. There would be actual Lambda code that serves as your business logic. And then there will be some language specific things like package descriptors and descriptions of your jars and things like that. If you're using Maven or Gradle, there will be constructs around that. But one thing we wanted to emphasize is there will be some README file which describes how you would go about packaging and deploying your application. So in this case, we have a deployment script for deploying the actual application to the AWS backend. But there is a packaging script also, which packages all the constructs into serverless artifacts and makes it ready for deployment. So this is an overall structure of our note-taking application that we are looking at for our server-based as well as serverless application. There is an infrastructure folder in here, and that infrastructure folder has all your CloudFormation template, which help you deploy your resources, as well as the contract, the Swagger specification that our application is going to adhere to. So let's quickly have a run through our Swagger specification. And we saw this visual representation of the Swagger specification. And this is an OpenAI specification of that visual representation. Like we saw earlier, there is notes endpoint, there is notes / particular title of the note endpoint, and then there are various HTTP verbs that we will be handling. I won't go into details of these APIs, but these are available for you later on if you need to implement applications like these. I'm going to skip past the internal details of these endpoints for sake of time. Let's go over the CloudFormation template now. In the CloudFormation template, and again, this is SAM-based CloudFormation template, and that is pointed out by this entry over here, which transforms the normal CloudFormation template into a serverless application model-based CloudFormation template. And it looks pretty similar to our standard CloudFormation template. There is a parameter section, there is resources section, and there is output section, similar to standard CloudFormation templates. Now, in the resources section, we have a bunch of resources over here. we have an API gateway endpoint that we are creating to serve our APIs. There are Lambda execution role and policy resources which are going to impart necessary permissions to the Lambda that is going to serve as bulk of your processing logic. And then there is actual Lambda function that is going to be implementing your business logic. Now let's go over some of the details about this Lambda function that we are describing over here. There is actual code URI which will be getting built and deployed. And then there are parameters like environment variables we would want to pass to the Lambda, as well as the execution environment. And like we mentioned earlier, we are using Node.js execution environment, but this could be different depending on the language and framework you are using. Then there are events that are triggering the Lambda that we are implementing most of our business logic in. And the event sources are, or here they are proxy API sources, but they could be coming in from different API endpoints depending on your application needs. So that was a quick look at the serverless application model based CloudFormation template. Let's have a look at the actual code. And to have a look at actual code of our API service that we have implemented, I'm going to switch to an IDE and then walk you through some of the important constructs in the code. Let's look at the actual code of our node staking application API that we saw earlier, how it looks like in serverless world. We are using TypeScript to implement this application. TypeScript is similar to JavaScript for folks that may not be familiar with TypeScript, except it adds type safety, which is very desirable in any large application. And this application has a package descriptor like any Node.js application, and it has scripts that need to be run to do different kind of activities such as build, deploy, package. And then there are dependencies. Now, we are using Inversify for our dependency injection framework, and so those dependencies are listed over here. Then there are some development type dependencies to describe things or import things that you would need during your development activities, such as your testing framework. We are using Jest as our testing framework, so that is specified as your dev dependencies. Now, the API implementation of node staking application has different components. There is config section, there is controller, there are model objects, then the actual service implementation, and then there is an entry point into this Lambda. So let's walk through how a typical web request coming in would flow through this code. So when the request comes in through API gateway, it will first come over here in the proxy layer. And that proxy, as you can see, doesn't do much. It just simply delegates that request to an Express.js application framework. And that's all that this proxy is doing. So if you're transitioning from your traditional application to a serverless application, this is the only change you would have to make. And like I mentioned earlier, if you find yourself making a lot of changes, re-architecting your application, maybe it's time to step back and look at what your application architecture needs to be, and make it the right application architecture depending on the 12-factor app principles we talked earlier. Then let's go into the Express.js application. After this point, it looks very similar, or in fact, it is similar to your Express.js application. And Express.js application has controllers to which all the REST requests are delegated. Now, any web framework would have these constructs. In Express.js, there'll be a controller section, but in Java applications, there'll be Spring controllers, and depending on the framework you are using, there'll be different types of controllers, but the concepts remain pretty similar. Let's have a look at the notes controller over here. And the notes controller handles the HTTP request coming in. So to create note, you will be writing a function like this to implement your note creation logic. And the controller, again, needs to be pretty lightweight. It just needs to handle the protocol translation from HTTP to your service tier. And keeping that principle in mind, what we are doing over here is taking in the HTTP request and delegating the actual implementation of business logic to this note service. Now, this note service itself is injected into this controller using the dependency injection framework we are using, and that injection happens over here. And this helps significantly in your development testing. So if you want to switch out actual service with a mock service, you could just inject a different dependency, and you should be able to test your mock service by replacing the real service with a mock service. Another thing you might have noticed is we are referencing the service by its interface. So note service is actually an interface and not the implementation. And that's what makes it possible to switch from real implementation to a mock implementation, or even different type of implementation of a note service. So let's go over the note service and see what it contains. So here's the interface. The interface, again, is another representation of the contract we saw earlier, except this is more of a business interface of your application that you are trying to implement. And then the implementation of this interface is in another class, and this is an in-memory implementation of a note service. For demo purpose, we chose to implement a note service in memory, but you could go ahead and implement a DynamoDB implementation of note service, or you could choose to implement a MongoDB implementation of note service. So this is a fully running application with all the different model components and different application tiers hooked together. So what I'm going to do is I'm going to start a local implementation of this application. And this local implementation is being very similar to the serverless world, can be deployed to the backend, and the actual deployment should look very similar to the local execution that I'm doing right now. So I have started a local server, and I'm going to make some requests to this local server. First request I'm going to make is a list request for the nodes that are there in the system, and I made a list request. And you can see over here I got a list of nodes that are present in the system. Similarly, I can make a find request and find a node by its title, and we would get back a node over here. So this is the demo of our serverless application in action. So we saw a serverless application in action. We saw how it looks like. Now let's talk about what are some of the best practices regarding serverless applications, some of the do's and don'ts that we have learned over the course of time, and some of the pitfalls that we would like to recommend when implementing serverless applications. So here are some do's about serverless application. So serverless application don't need to be very different from your traditional applications if they are built using some of the best practices out there of any application development or any API development. And 12-factor applications are some of the guiding principles for how to make your application scalable, and performant. So if you follow these best practices using 12-factor app principles, you should be able to build good APIs using serverless stack. In serverless world, you should not assume any local storage. So everything tends to be ephemeral. So don't assume there is some storage in your compute engine, because that compute engine can be completely swiped away from your computation without any notice to you. So make sure your application is as stateless as possible. And then generally in a typical application, there are scenarios where you have expensive objects that need to be created. There are connections that need to be established to external databases. So in those scenarios, try to create those expensive objects and connections to external data sources outside the event handler of a serverless application. So this is something different from your traditional application. In traditional application, you could instantiate these objects anywhere you want. But in a serverless world, you have to make sure that these expensive objects are instantiated outside the event handler. And then in serverless world, don't assume that everything needs to be done in the cloud. Go ahead and do your local development and testing. Make sure your application works fine locally on your laptop or on your computer so that you can iterate faster. You don't have to, for every little change, deploy it to serverless backend and see it happening in the serverless backend. You can very well iterate faster, do it in your IDEs, do it in your local terminal, run unit testing locally, and make sure your applications work perfectly fine locally, and then go ahead and deploy it to the serverless backend. This is something, end-to-end integration is something we learned at the hard way, that it becomes very important in serverless world. Make sure that all your stack is behaving as expected earlier on in your API development or application development lifecycle. By end-to-end, what we mean is your UI tier, your front-end facade, your back-end services, your persistent layer. Make sure all these interacting components, they work and they are performing to your requirements. Profile each part and make sure that you are not hitting any bottlenecks at any of these in these stages earlier on in your application development lifecycle. Then profile your application bottlenecks. Use standard profiling tools such as AWS X-Ray or App Dynamics, or there are Java-based profiling tools. Use them to your advantage. Some don'ts about serverless application. Don't architect your application differently for serverless. If you find you're architecting it differently, there is something disconnect between what you were doing before and what you're doing in the serverless world. If you are following the 12-factor app principles in serverless world, then probably your application before was not properly architected, and that could be a good thing. You are re-architecting your application and then you are transitioning it to serverless world. But if your application is well architected, keep the architecture pretty consistent with your old application architecture. Significant logic in API gateway layer. This is something we have seen come up over and over again, and there are conflicting opinions about this, but our recommendation tends to be that try to avoid putting significant logic, and definitely avoid putting business logic in API gateway layer. Let your application logic handle most business logic. But there are schools of thoughts which says things like validation and marshalling and marshalling of parameters can very well be done in API gateway. But we found that it can get hairy sometimes, and you might end up spending way too much time than necessary for your application development. If you find yourself implementing workflows, probably serverless is not a good fit for the use case. Use step functions for implementing workflows. Don't implement workflows in lambdas. And then if you're implementing a lot of long running processing type of applications such as media rendering applications, encoding applications, those also tend to be not good fit for serverless application development. Use containers for that. With that, let me transition to Rahul to talk more about serverless CI/CD.
Thanks a lot, Atul. That was really informative. So let's talk about some of the AWS services that fall under the serverless CI/CD spectrum. The first service that you see is Code Commit, and Code Commit is a fully managed source control service that you can basically use to store your private Git repositories. You can store almost anything from the source code to binaries, and the best part is that you can reuse the same Git tools that you have been using, so you don't have to change anything in your in the way you develop. So the second service you're seeing is Code Build. Code Build is a fully managed build service that you can use to compile source code and do unit and integration tests, as well as you can also create a software artifact that can be deployed to your production, development, or test environment. The third is Code Deploy, and Code Deploy is an automative software deployment service that can deploy your software to a variety of compute instances such as EC2, Lambda, or even if you want to deploy a software on your on-prem instance, you can absolutely do that with Code Deploy. So we have seen the source code, we have seen the build, and we have seen the deployed. To orchestrate all that into a pipeline, we have a service called Code Pipeline that basically does the same thing. So you can have your source code repository as a code commit, you can have your build service as a code build, and you can have your deployment done by Code Deploy, and Code Pipeline will help orchestrate all those things for you.
So this is great, Rahul. This is nice. But aren't there existing products out there which handle things like Code Pipeline? You could do Code Pipelines even in Jenkins. So why would you need something like Code Pipeline if you're already doing things in Jenkins?
That's a very interesting question. But the thing is, the one thing that's common across all these services is that there is no server to manage.
Okay.
It's all serverless. So you don't have to worry about patching your servers, installing software updates. Then there is so much of hassle that goes into building the servers, managing them, scaling them. So it's a lot of overhead, operational overhead that you would probably not want to take, and you would probably be interested in just building a pipeline that takes care of all those things. And the AWS CodeStar services basically helps with all the operational overhead.
Nice, makes sense. So you're saying no more headaches of Jenkins server going down.
No more servers. Now we'll do a walkthrough of a CI/CD pipeline. In the CI/CD pipeline that will show, we are using Code Pipeline to orchestrate everything. For the source code repository, we are using Code Commit. So we'll check out the source code from Code Commit. We have a build stage that does the linting, it runs the unit test, and then it packages the software and deploys it in S3. Then we move towards the staging stage where we deploy all the artifacts that we did in the build to the staging environment, and then we run the integration test on top of it. And finally, once all the tests are passed and the staging is cleared, we deploy the application to production. So as you can see on the screen, this is one of the pipelines that I have created for deploying a REST API. So what Atul earlier showed in the demo, it was a notes application, and it was a very simple CRUD based application. I wanted to take it a step further by showing that you can also deploy a complex application or a complex REST API using the CI/CD pipeline, and it's the same process. So what we have in front of us is a serverless application that is basically built around asset management for IoT devices, and we'll go ahead and we'll deploy this using the code pipeline. So this is the console for code pipeline. As you see here, we have our source code, which is code commit. Then we have multiple steps around building, staging, and then deployment. So I'll just go ahead and I'll release the change, and it generally takes around 20 minutes for this whole pipeline to finish. But what I'll do is I'll do a walkthrough of all the steps as to what's happening at which step, and hopefully if we have time, then we can probably see this whole pipeline getting to the completion. So I'll go and release the change. As you see, now my pipeline has started, and what it'll do is it'll go ahead and it'll check out all the code from code commit. So as you see that it's already started building and checking out all the code from code commit. Next is the build stage. So for build, we are using code build. Let me go back to our source code. As you see here, we have the similar structure what Atul showed you. It's just that it's a little bit more complex application. So we have all the business logic residing within the application module, and to host that application, we have two options. One is serverless and server. So you can deploy this application either on containers or on Lambda. For this demo, we are just focusing on the serverless part. And serverless, if you see, will contain all the CloudFormation templates of how to deploy API gateway, Lambda, and all the business logic that will be contained in the Lambda. And then we have finally the CI/CD module, which goes ahead and builds the pipeline for deploying the REST services. And within that, we have this code pipeline YAML. So as you see earlier that we have the build process, and we have a build project here created. And what it does is that it runs few git commands and it goes ahead and does the build. So one good point to understand is that if you're using code commit with code pipeline, it doesn't check out the project as a Git project, but it just checks out all the files as it is. So if you probably want to add some submodules or do the Git initialization, so you have to do that as part of the pre-build process. So that's where you see that I'm running all the Git initialization and adding the submodules. And then finally we do the build where we go ahead and do the linting tests, we do the run the unit tests, and once everything gets passed, we create the artifact and deploy it in S3. So as you see that my code commit is still in progress, but once the build gets completed, it moves to the staging stage. So as you see that within the staging step, we have multiple progressions going on. So the first part is basically building the packaging the CFN. So if you are familiar with the CloudFormation, there is a command to package all the CloudFormation templates and create it into an artifact, and then you can deploy it into S3. So this script is basically doing that. Then we create the change set in the CloudFormation and then deploy the change set in the CloudFormation. Once it completes, we run the integration test. So as I go back to the integration project, you see that we have an integration test project where we run some of the BDD tests. So we use BDD, which is a short form for behavioral driven development, and it's a very popular methodology to do the testing. We currently use a very common framework called Cucumber for all the BDD tests. And once the integration tests passed, then we go ahead and publish the software artifact into an S3. that is ready to be deployed to the production environment. And then in the deployment stage that you see further, we repeat the same process again, where we package the CFN, we create the CloudFormation chain set, and then we finally execute it. And this pipeline that you see is just a small representation of what you can build. You can actually go ahead and add more changes. If, for example, a lot of customers say that before deploying my code to the production environment, I want some sort of a human interaction or some sort of a gate where we can do the review for the code. So you can absolutely add all those things. The code pipeline provides you with all the flexibility that you think you need to build that whole continuous integration and continuous delivery pipeline. So as you can see that we are still going through the code commit process. This whole pipeline takes around 20 minutes to complete. So now, since we have seen the demo, let's talk about some of the best practices for building a CI/CD pipeline. Security, security is job zero for AWS, and it should be for all the developers. The idea here is that you should not even think about security of the individual parts. So for example, you have a source code repository, you secure the source code, that's good. You have a build server, you maintain the security of that build server, and then you have a deployment server. But the idea here is that you should also go a level up and think about the security of the whole pipeline, how the artifacts are flowing, how the build server is getting the source code and doing the builds and running the integration tests. So you should think about security holistically rather than just the individual components. Logging is a first-class citizen, and you should be logging each and every step throughout the pipeline. So you should be able to not only find out when the pipeline was kicked off for deployment, but also if there are some errors along the way, you should be able to log each and every step. And previously, logging used to be an expensive operation because of all the storage costs, but with cloud, the storage has become so cheap that now you can log each and every step without worrying about the large costs for storing the data. Notifications are also very important. So for example, if you are doing any builds or if you are doing integration or unit tests, you should be able to get notified when something failed or something even completed. There should be notifications and subscriptions set up, and then we can worry about setting up the subscribers later on, and you can even decouple the subscribers from the notifications. The idea of failing fast is the integral part of building a pipeline. So we have a lot of tests like unit tests, integration tests, QA tests, and those are integrated all along the pipeline. The idea here is that as soon as something fails, you should stop or you should fail the pipeline. You should not push the buggy code towards the production environment. And finally, all the environment updates should be released via pipeline. There should be no human interactions along the way. Build once, push through the code pipeline. The idea here is that you should spend more time building the pipeline, and once the pipeline is built, you should then repetitively do all the updates, all the releases through that pipeline. So don't worry about spending a lot of time in building the code pipeline, because once it's built, it's a repeatable process that will save you a lot of time in doing the deployments. So use short-lived feature branches. The idea here is that now with new technologies, creating branches has become a very inexpensive operation. Now you don't have to worry about creating branches and then your whole code is not copied along with it. For example, Git, it provides you with pointer records. So whenever you create a new branch, you can check the code. If everything looks good, you can just basically go and merge it with the main branch. So I would highly recommend that any feature request you're working on, create a separate branch, work on that. Once everything looks good, merge it with the main branch. And then run all the tests locally first. So rather than kicking off a pipeline and finding it out later, figure out whether your code that you deployed locally is good enough or not. And once everything looks good, then merge your code and kick off the pipeline. Only build what has changed. What we found while working with some of the customers is that when you are building 3 or 4 resources and suddenly you just kick off a pipeline update for one resource, all the other 3 resources also get built. Don't do that. Just try to build whatever has changed and leave the other resources as it is. And then finally, and very important, version control everything. That's a big help that every developer can get while doing the version controlling themselves. So we talked about some of the best practices. During the journey, Atul, there were a lot of lessons that we learned, and I would like to talk about some of them. So I know you briefly mentioned about not adding a lot of logic in the API layer, and I completely agree with that. We have a construct called mapping templates in API gateway. I would recommend that if you don't have a real big desire for using the mapping templates, don't do that. Just use the proxy layer integration with Lambda for the API gateway. A good example is, we were working with a big healthcare customer, and what we found was that they had some legacy backends, and we started working with mapping templates, and it can become complex real fast, real soon. So try to avoid that if possible, and try to use the proxy layer.
Totally agree.
Another good thing that we found was that the timeouts for API gateway and Lambda were different, and we got burned because of that a lot. So API gateway has the hard limit on 30 seconds for the timeout, whereas Lambdas can run for 5 minutes. And especially if you are nesting different microservices, then it can become real difficult to debug. So try to make sure that you account for each and every service timeouts.
Right, and tracing where the execution failed with different timeouts can be really nasty.
Yes.
We learned it the hard way that debugging those problems can be a little bit tricky.
Then use SAM Local for local debugging. SAM Local is a very good tool. Even if you are working out of an airplane where you don't have internet connectivity, you can just test out your code locally, and once you have the connection, you can push your code to start the build. Lambda environment variables are very important, and I would highly recommend that use that for all the external dependencies. So if anything changes, you don't have to change those things throughout the code, but just changing the environment variables and just adding a pointer record for that in the code. Initialize external connections outside handler. So for example, if your Lambda is making a connection call to a database, keep it outside the handler so that you can reuse a lot of the good components about container reuse feature set for the Lambdas. And finally, reduce your cold start impacts. So choose your language pretty well. So for example, if Java is known for providing more higher cold starts compared to Node.js and Python. So if you really don't have any hard requirement of using Java, I would recommend use Python or more lightweight frameworks. And even if you are using Java, right, I would recommend that try to use some lightweight frameworks like Dagger or Juice rather than Spring. That will help reduce your cold starts further.
So the reason for that is Spring tends to do a lot of its initialization at runtime. Juice and Dagger, on the other hand, tend to do the dependency injection initializations at compile time, and that saves a lot of time during cold start, and every second counts during cold start. And that's why we found that response times can be improved significantly by using lighter weight frameworks like Dagger and Juice.
That's a very valid point, and yeah, I would highly recommend that choose your language pretty nicely, because cold starts can provide some impact in your microservices. And with that, we approach the end of our session. I hope you guys learned something new, and those tips and tricks that we provided would be helpful for your code development. So happy time coding. My name is Rahul Sareen.
I am Atul Bargaze with AWS.
And we work in the IoT Professional Services team. Thanks a lot for watching.